Welcome, welcome, welcome. Welcome to this episode of CSEC Physics with me, Marvin Lee. Today, as you probably can see on the board behind me, we will be looking at linear momentum. Momentum again, I know it might not be that glamorous or interesting, but we have to look at momentum, we have to look at collisions. We have to work some problems, examine some scenarios, and discuss a few things. So, I hope you're ready for some fun, for some physics, and for some maths. Again, welcome to this episode of CSEC Physics with me, your host and teacher, Marvin Lee. Now, in this episode, we have to look at linear momentum, but we have to look at linear momentum in terms of collisions. Now, a collision is really simple. Anytime you have an object with some velocity coming into contact with another object, whether the other object has velocity or not, that is basically what a collision is. Collisions are everything from hitting a cricket ball, vehicles on the road, somebody pushing you, somebody punching you, you punching someone, to the ever famous Guyanese thing, you know, where you come in a minibus and you're going to an empty seat and Guyanese do that thing where they hit the seat. Yeah, that's a collision as well. Now, collisions are very, very, very common. Like I said, as long as one object has velocity and it comes into contact with another, it is a collision. The level of violence or severity of the collision depends on the velocities involved. There are two main types of collisions, just two. We have inelastic and we have elastic. Now, the cool thing is these collisions are really easy to understand. Inelastic collisions are essentially real-world collisions that happen generally in life. When two objects collide, energy is usually lost. Now, this energy is primarily lost as sound, but there are cases, and it's far more common than you think, where deformation occurs, where the object changes shape. Now, this causes there to be more energy before the collision in the entire system and then less energy after, because if I do this is a very simple collision. I'm clapping and a sound is produced. Energy is lost as sound. Now, there is temporary deformation of my hands because they kind of press together, and that squeezing together of my palms causes them to be deformed temporarily, but it's not a permanent deformation. If however, a car hits another car or a post, or let's say you drop a metal can, a can of soda, and it hits the ground, that will produce some, or most likely should produce, some form of permanent deformation, and energy is lost as a result of these things. So inelastic collisions are simply defined as collisions in which kinetic energy is not conserved. Okay? Now, there are two important things about every collision. There's the behavior of the objects before they collide, and then there's the behavior of the objects after they collide. Before they collide, they have a certain amount of energy, and then after they collide, they have, again, a certain amount of energy as well. In inelastic collisions, there is a difference between the total energy of the system before and the total energy of the system after that collision. So that's how we know they're inelastic. Onto elastic collisions. Now, elastic collisions, I call them cartoon collisions. I've been looking at cartoons all my life. I love them. And everybody knows that no matter what happens, in my personal favorite cartoon, Tom and Jerry, no matter what happens to Tom or Jerry, they go back to how they were before the accident happened. I've seen Tom turn into a table. Tom has been hit with a hammer. He probably got blown up a few times. But no matter what happens, Tom always goes back to how he was before the collision happened. And that's as, well, I shouldn't say as close as we come, but that's exactly what happens in an elastic collision. There's really no change to the shape of the object. How the objects are before they collide is exactly how they are after, and no energy is lost. No kinetic energy is lost. So the total energy before they collide is the same as the total energy after they collide with elastic collisions. So remember, in elastic, energy is lost. These are real world practical collisions. Elastic collisions, no energy is lost at all. There is no energy lost to sound, there's no energy lost through deformation. The objects essentially remain just as they are. Now, the best real world example of an elastic collision is what Guyanese call pools, or if you're playing billiards. The objects don't become deformed. If you hit one pool ball or billiard ball into the other, it doesn't cause deformation. Of course, there is sound, but that doesn't cause a tremendous change in the velocity of the objects. Also, if you notice, you don't play billiards or pools on a rough surface. The surface is incredibly smooth. The surface of the balls be incredibly smooth as well. And this is why you can say the collisions are close to, or as close to elastic as possible. So, recapping very, very quickly. In elastic, energy lost. There's a difference between the total kinetic energy before and the total kinetic energy after. In elastic collisions, there is no energy lost. The total energy before the collision is the same as the total kinetic energy after. These are the two types of collisions. Now, it would please you to note that we only look at one. We only look at elastic collisions for the simple reason that they're easy to analyze. It's easy to assume that no energy is lost. When you go into actually looking at what causes energy loss and how energy is lost, it becomes a bit complicated. For example, if you're looking at, I'm sure you probably see, well, actually no, the advertisements don't come the same. But it was once a point in time when a lot of advertisements with cars had the whole crash test video, and it showed you the car crashing into the wall, and they had the crash dummies, and they showed you how the dummies would move in the car. If you look at a car crashing into a wall, what happens is essentially the people at the back are moving or start moving a little after the people in front moving forward, and the people at the back come to rest after the people in the front. The back of the car sometimes comes off the ground. All of these little things, all the areas in which energy is lost, would have to be analyzed if we are looking at an inelastic collision. If, however, we're looking at an elastic collision, we can just assume that there is no energy lost, and those things don't need to be considered. So for ease of analysis and for simplicity's sake, for CSEC, we only look at elastic collisions. Anyways, it is time for us to do some calculations and some analysis of a few scenarios. But before we do this, the analysis of these scenarios, we have to look at something called the principle of conservation of linear momentum. Now, we're only looking at collisions that happen along a straight line. If you would remember, we did look at straight line motion. So we're going to look at collisions on a straight line where the objects are moving along the same straight line, either in the same or opposite directions. And there's so many things that can happen. Let me give you a few scenarios. For example, you could have two objects heading in opposite directions, and when they collide, they just totally stop moving. What happens then? You could have the scenario where you have a slow object being pursued by a faster object. The faster object hits the small object, and the two essentially combine to form one new object, and they move off. You could even have the case of a stationary object being hit by a moving object, and the stationary object moves off while the object that was previously moving comes to total rest. So many scenarios. And you might be thinking, okay, what do we do with these scenarios? Well, we use something called the principle of conservation of linear momentum. It's a long name, I know, very long. And it simply says that the vector sum of momentum before a collision, is equal to the vector sum of momentum after a collision. Meaning, if you add up, taking direction into consideration, the total momentum before two objects collide, and then you add up the total momentum of these two objects with direction considered after they collide, by this principle, these two values should be the same. There is a condition. The condition is that the collision be elastic. That is, kinetic energy is conserved. If this condition is not met or it's not assumed, then the principle of conservation of linear momentum, that's such a long name, does not apply. So let me go over again one more time. The vector sum of momentum before a collision meaning you take direction into consideration, is equal to the vector sum of momentum after a collision. Again, direction is considered, as long as the collision is elastic. That is the principle of conservation of linear momentum. It's time for us to get some examples. Grab a pen, paper, your calculator, follow along. Welcome back. I hope you have your books, pencils or pens, and your calculators, because we have a nice little example to look at. Now, I use spheres to represent my masses because they're easy to draw, and I'm not going to draw any stickmen for you folks to laugh at my stickmen. And I indicate my velocities with numbers and arrows for direction. Now, the directions be very, very important. So, we have example 1 here, and I must add that this is how the system, and by system I mean the masses and the objects involved, behave before collision, and then this is how they behave after. Before and after, before and after. Now, by the principle of conservation of linear momentum, by this principle, if this collision is assumed to be elastic, the vector sum of momentum here is the same as the vector sum of momentum here, meaning whatever is the total momentum over there should be the same as the total momentum over here. So just let me get you used to how I indicate things. The masses are indicated in the spheres, and the velocities and their directions are indicated above. If you notice, 0 meters per second. Now I don't need to give a direction to 0 meters per second because 0 implies it's stationary, it's not moving. Over here we have again another 0 meters per second, and this is also not moving, but over here we have a question mark, meaning we do not know what happens to this 1 kilogram mass. Well, let's find out. So if we remember from last lesson, we define momentum as mass by velocity. It would imply that each object in this entire scenario has a momentum, mass by velocity. 2 by 4 is 8 kilogram meters per second. Well, 1 by 0 is 0, 2 by 0 is 0, and we have no clue what happens here because we do not know the velocity. So this question mark, you know what, this is not a good idea. Let me not use a question mark. Let's call the momentum of the 1 kilogram mass Z. Yes. Okay, the question mark is velocity, and I don't want to confuse anyone at home. So the question mark is velocity, the unknown momentum is Z. So by the principle of conservation of momentum, if we add up these values and we add up this value, they should be the same. Total momentum before, total momentum after, and the assumption is made that the collision is elastic. Now, some math for you. This here, I will assume that this is positive. Okay. Now, by saying this is positive, it means that this direction going to your right is positive. Okay. I'm going to add this here, and my total on the side, this side, which is the total before they collide, is 8 kilogram meters per second. Now, it means that my total on this side, by the principle of conservation of linear momentum, take a breath before you say it, the total here should be 8 as well. So my limited mathematics skills tell me that 0 plus Z is the same as just Z. So the momentum of this object, which is represented by the letter Z, the momentum of my 1 kilogram mass is 8 kilogram meters per second. What does that tell us? Again, because this value is positive, it tells me that this 1 kilogram mass is moving in the same direction as this, because we took this as positive. So since Z is also positive, it means that this object, or 1 kilogram mass, is also moving in that direction, which is the positive direction. Now please note, I didn't take it as positive because of the number line. I just took it as positive because It was the only value we had over here that was a non-zero value. It has nothing to do with the number line, so just putting that out there. So this Z is the momentum of the 1 kilogram mass. But my unknown here, the question mark, was really asking not for momentum, but it was asking for velocity. Now looking at this equation, we can easily see that momentum divided by mass gives us velocity. So the velocity of this, the velocity of our 1 kilogram object, will be equal to momentum 8 kilogram meters per second divided by 1 kilogram. Yes, the units do cancel out, and the answer we get is 8 meters per second. So this velocity would be 8 meters per second in that direction. Simple. Total momentum before, total momentum after. This applies because the collision is assumed to be elastic, and we simply rearrange this formula, use it here to get our value of velocity, which is 8 meters per second. And this is our first example. You can always check over, please check. And you can even make up your own examples if you want and change the numbers around, but you're going to see that it should work out, or it should be worked this way. Now, before I move on, there are times when a formula is given, m1 v1 plus m2 v2 is equal to something. I hope I'm getting it right. But I usually avoid the formula for the simple reason that it pays to actually be able to analyze the situation on its merit, because sometimes that formula doesn't always help, because there's some scenarios where you could even start off with a single object and then you can end up with 2 separate parts. Yeah, that's actually an example, and we will look at it. I think that will be our last example. So for now, folks, do check over, tell me if I'm right, and let's move on to example number 2. Having changed the color of my chalk, and through the power of editing, I guess, this is the second example. Now, the first example, we had one object at rest and the other one hit it, and then that one came to rest, and the first object that was at rest, moved off. Here is different. We have 2 objects, one moving at 6 meters per second to the right, the other moving 6 meters per second to the right as well, and they collide. Now, just so you might be wondering, like, why did they collide? Sorry, I said 6 meters per second for both. I think, anyways. This is way faster than that, all right? So essentially, one runs into the other from behind. That's what happens. Now, after they collide, the 2 kilogram mass has a very large increase in velocity. We want to find out what happens to the 3 kilogram mass. So again, principle of conservation of linear momentum is applied because we assume the collision to be elastic. Kinetic energy before is equal to total kinetic energy after. And we never ever lose sight of this. Momentum is mass by velocity. So 6 by 3 is 18 kilogram meters per second plus 2 by 1 mass by velocity. 2 ones are 2. And let me see, magically 18 and 2 give us 20 kilogram meters per second. Now, it means that this 20 kilogram meters per second should be the total momentum of these 2 objects after they collide. Again, we assumed the collision to be elastic. So let's call the momentum of the 3 kilogram mass B. Okay, B. 2 sevens are, last I checked, 14. Good. So it implies that B plus 14 is 20. In other words, 20 is equal to B plus 14. Now, in primary school, when we were given questions like this, if we got them wrong, we would have got a couple lashes. I hope I don't deserve lashes for getting this one wrong. This B is 6 kilogram meters per second, because 6 plus 14 would give us 20. If we want to do it the correct way, we could write it out. When we do the transposition, we end up with 6 kilogram meters per second is B. And that is the momentum of the 3 kilogram mass. Again, since these two objects are traveling, well, in the same direction, we add the momentum of the two. We don't need to subtract anything because they're not going in opposite directions. Now, since this value is positive, what it implies is that this 3 kilogram mass is moving in the direction, like everything else, to the right. But my guess is it's not moving as fast as it was here. So if I ask what is the velocity, which is exactly what this question mark implies, I mean, how fast is this thing moving? We just rearrange the formula. Again, momentum P is mass m by velocity v. Therefore, velocity v would be momentum P divided by mass m. Momentum is 6, mass is 3. 6 divided by 3 would give us 2 meters per second. As we can clearly see, if we do the math, the total momentum here is equal to the total momentum here, because we assume the collision to be elastic. And our directions are all to the right because all our values are positive. And again, it has nothing to do with the number line. I could have said minus 18, minus 2, minus 20. I could have done that. And over here, I would have had minus 6 and minus 14. You can take any direction, going to the left or going to the right, as positive. Okay, it doesn't matter. I just find it easier to work with positive numbers. So the principle of conservation of linear momentum helped us to find the momentum, B, which is 6 kilogram meters per second, and our velocity, which is 2 meters per second. This is our second scenario. So to check over, ensure I'm right, I will change the color of my chalk, write another example on the board. We have 2 more to do. See you just now. Having changed the color of my chalk again, we come back with the third example. Now, the first example, quickly recapping, was one object hitting a stationary object. This example is just 2 objects traveling in opposite directions. Now, for fun, I used easy numbers. I used the same velocity. And then we have what happens after the collision and our little unknown. So, starting with what happens before they collide. Again, momentum, I'm gonna write it for the third time. Mass by velocity, mass times velocity. 8.5s, last I checked, is 40 kilogram meters per second. Okay? Now, mass by velocity 4.5s are 20 kilogram meters per second. You would notice that I have put no sign. The velocities are in opposite directions. Therefore, we subtract. What this means is that I've taken that side as positive, and this side will obviously be negative since it's the opposite direction to that. This means 40 minus 20 gives us a grand total of 20 kilogram meters per second. After they collide, the 8 kilogram mass still moves in the right direction with a velocity of 2 meters per second. So let us see what happens. A2 is B, 16 kilogram meters per second, and let's call the momentum of the 4 kilogram mass H. So since it's unknown, we just add it. Again, assuming this collision is elastic, by the principle of conservation of linear momentum, this 20 is equal to this 16 plus h. So, doing a little math, we quickly figure out that if 20 kilogram meters per second is equal to 16 kilogram meters per second plus h, it would imply that h is 4 kilogram meters per second. Again, we carry this across. 20 minus 16 gives us 4. So the momentum of H is 4, but please note, it's positive 4 plus 4. That would mean that this mass is now moving in the positive direction. So it's moving to the right. And again, please don't think that always moving to the right is positive. Not the case. I just choose numbers that give us these values. So the velocity of the 4 kilogram mass from this equation, the velocity of this would be the momentum divided by the mass. 4 divided by 4 gives us 1 meter per second in that direction. So opposite directions, we subtract, and over here we add this to the unknown, equate it to what we got there. We do our algebra. Our momentum is 4 kilogram meters per second in that direction. Therefore, our velocity is 1 meter per second in that direction. This is our third example. Now, we have one more example to look at. One more example. And I'll change my chalk, write my example on the board. I'll be right back. Chalk changed, example on board changed. Let's go. So here we have an interesting scenario, a possible scenario, okay? We have two objects of different masses traveling in opposite directions that collide and then form one massive object, okay? This can happen as well. Now, please note, outside of this happening, you could actually have the opposite. You could have one object, for example, like exploding and creating multiple objects. So the reverse can happen. 2 can become 1 and 1 can become 2 or more. Now, using the ever faithful formula and assuming the collision to be totally elastic, momentum is mass by velocity. 4 by 2 gives us 8. What a horrible 8 meters per second. Look at me sinning. Father, forgive me. It's supposed to be kilogram meters per second. Oh well, we all make mistakes. Children, don't be ashamed to make yours. So 4 2s, 8 kilogram meters per second, and 10 by 5 is 50 kilogram meters per second. Now, they're traveling in opposite directions. Okay, if I take this as positive, all right, if I take this is positive, going right is positive, and I take this as negative, I will end up with minus 42 kilogram meters per second. Okay? Yes, you can have a negative value. Don't be scared of it. So, I have no clue as to what happens with this. There's just one object now. Now, I put 14 there because I kind of give away what happens. If these two objects, 4 kilograms and 10 kilograms, if these two combine without losing any mass, the new mass of the object, the single object, is now 14 kilograms. Okay, that's the first thing. The second thing is that because there's only one object, we don't know what happens here. We have to depend on the principle of conservation of linear momentum to explain this. Now, this minus 42 kilogram meters per second is essentially the momentum of this 14 kilogram object after the collision. So what it means is that this 14 kilogram object, is moving to the left, like Beyonce said, and we just have to work out its velocity. Why is it going to the left? Because we took this value here as negative. That's why we have a negative momentum here. This direction is negative, this momentum is negative. The total momentum is negative, therefore this moves in the negative direction, which for the sake of this example is to the left. Anyways, again, applying the formula that momentum is mass times velocity. To find the velocity, we divide momentum minus 42, not just 42, kilogram meters per second by 14, 3 10s 30, 3 4s 12. I do believe, if my math is correct, this is 3 meters per second. So our object, our new object, moves to the left at 3 meters per second. Total momentum before they collide is the same as the total momentum after. So that gives us our 42 over here. Dividing by 14 gives us our 3, which is our velocity. These are 4 of the most common examples that you're going to find. Okay? These are the 4. Now, the cool thing is, you just have to remember that you apply the principle of conservation of linear momentum. You don't need to do anything fancy. Mass by velocity for each object, with direction taken into consideration, you find your total, you equate it to either before they collide or after they collide, you find your unknown momentum, you divide by mass to find your unknown velocity. That's what you do in most cases. So, to quickly recap today's lesson, inelastic collisions are collisions in which kinetic energy is not conserved. Elastic collisions are collisions in which kinetic energy is conserved. And the principle of conservation of linear momentum states that the vector sum of momentum before a collision is equal to the vector sum of momentum after a collision, provided that kinetic energy is conserved. This is what we apply today. This is what I hope you learned today. And I will see you next time on the next episode of CSEC Physics with me, Marvin Lee. Take care, stay safe, enjoy the holidays.